Hello ladies and gentlemen, welcome again to Superposition, our final part of our tutorial video. Now today we are going to do stationary waves. The first question in question 15 is about stationary wave with a fixed length, but they want you to find out which harmonic it is. A wire of length 1.8 meters is fixed at both ends. Now, the fact that it is fixed at both ends means that the boundary condition is a node at either end. Now the tension is such that when a wire is plugged, the transverse wave of 300 meters per second is propagated by reflection at both ends and 3 antinodes are formed. Now supposing that you didn't have the answer here, how would you actually solve this question? You solve this question by putting 2 nodes at either end. We know that there will be 2 nodes because these are the boundary conditions. Then we have 3 antinodes in between. Antinode, antinode, antinode. Now, in between the antinodes, you know that there must be nodes as well. So there's a node here, a node here. And that way you can draw the standing wave, okay, form like that. Okay, so it's a lot harder than it looks to draw the standing wave. So I'd like you to practice. Now this is the first half cycle of the standing wave. So that means that the wavelength, as you can see, is over here. Okay, so from the wavelength stretches 3 nodes. Okay, now let's draw the other half of the standing wave so that we can complete the diagram, and that's the other half of the standing wave done. Now, so we can see that 1.8 meters, the length of 1.8 meters is 1.5 wavelengths. So the wavelength will actually be 0.6 meters. What am I saying? The wavelength is actually 1.2 meters. Alright, so the transverse wave speed is 300 meters per second, so this is V. Right, this is L is 1.8. Alright, so now we can use V is equals to F lambda in order to find the frequency. F is equals to V over lambda is 300 divided by 1.2. That is 250 Hertz. Now, those of you who are asking, wondering which harmonic this is, let's take a look at 3 over 2 lambda. 3 over 2 lambda indicates that this is the third harmonic, which means that the fundamental frequency is actually 250 divided by 3. The fundamental frequency will be 250 divided by 3 Hertz. Okay. So that's not needed for this question, but you should always be thinking of what's the fundamental frequency every time you see a question like that. Okay, so now we're done with question 15. Let's move on to question 16, which is a different kind of stationary wave question. Question 16 is one where the frequency is fixed, but the length of the wave, the length of the tube can change. A student performed an experiment to measure the speed of sound in air. He emits a sound frequency of 600 Hz, that's F, placed in front of a reflector R. The fact that there is a reflector means that there is a standing wave. A sensitive microphone M is then moved between R and S, and then mark the position on the microscope. The first peak signal means that the first antinode will be detected when M is located at 130 mm mark. So this is the first position. The third peak signal, the third antinode again, will be detected when M is at the 698 mm mark. So we're going to form the nodes and antinodes of the stationary wave formed between the 2 positions of the microphone. So this is the first peak signal. It's moved from R to S. So here is a speaker, right? Over here, here's a speaker S. Then here is a reflector R. Here's a reflector R. Okay, so we don't know where the microphone is exactly, but this is the position of the microphone. The position of the microphone is 130 mm, and we know that it is at the antinode. This is the first peak signal. Then the next one will be a antinode. The second antinode will be here, and then the third antinode will be over here, where the microphone is, and this will be 698 millimeters. Okay, so this is the antinode, so we'll draw like that. Antinode we draw like that, antinode we draw like that. Then in between there must be a node, so we put a node here. Okay, so we can draw the antinode like this. Okay, and then to complete the diagram, we can draw the other half of the standing wave. Okay, so now there are 3 antinodes. Now you can see that actually between these 3 antinodes, it's actually one wavelength. Okay, it's actually one wavelength. Alright, so that is my drawing. Okay, as the microphone is moved from R to S, it starts at the antinode, and then the third antinode it stops. So calculate the positions at the 130 and 698 mm where the signal is minimum. So this is 130, and then this we can calculate half over here, and then we can calculate 1/4 over here. Okay, so basically it's easy. You just divide the distance between 130 and 698 divided by 4. Okay, so let me first find the average between 130 and 698. So let's find the second antinode. The second antinode will be 130 plus 698 divided by 2. Okay, and that makes the second antinode position at 414 mm. That means that let's say this is the first node and this is the second node. So the first node will be at 130 plus 414 divided by 2. And in the same way, the second node will be at 414 plus 698 and divided by 2. So this position over here, this will be at 272 mm, and this position will be at 556 mm. So you can see that once you draw the standing wave, the question becomes really easy to solve. You can solve it using primary school math. So let's calculate the speed of sound based on this experiment. Okay, so we can see that the wavelength will actually be 698 minus 130. This will be 568 mm. And then we know that the speed of sound V is equals to F lambda, and the frequency of the sound is 600 Hertz, which was obtained up here. Okay, the frequency was given to us earlier, and the wavelength is 568 millimeters, which is 0.568. So this gives us 341 meters per second. And this is how we will solve a standing wave question. Always ask yourself, what is the wavelength? First draw the wave first and ask yourself what's the wavelength, and then V equals F lambda to solve it. So this is the end of this question. Let's move on to the next question. Question 17 is one of the more challenging questions. Okay, a ship is at X. So let's draw the ship over here. This is the ship, all right. It's equidistant from two shore-based radio transmitters P and Q. So the distance here is the same as here. All right, as shown in the figure, both transmitters operate at a wavelength of 300 meters. Okay, I'm not sure what kind of radio signal has a wavelength of 300 meters and radiate signals of equal amplitude. The ship at X detects 0 signal amplitude. Now, when you detect 0 signal amplitude, it means that destructive interference has taken place. Right? So destructive interference has taken place. What information does this give about the signals from P and Q? So remember that whether destructive or constructive interference takes place depends on two factors: the initial phase and the path difference. Okay, in this case, the destructive interference occurs even though the path difference is 0. So if the destructive interference occurs even though the path difference is 0, that means initially the sources were in antiphase. That means the sources were broadcasting initially in antiphase. Because if the sources were initially in phase, then if you have a 0 path difference, the result will be constructive. This is one of the first things that we learn in the first part of superposition. Okay, and you can see that it's being used over here. So the signals from P and Q are pi radians out of phase, or you can write are in anti-phase to each other. The ship moves in a straight line from X to Y. Throughout the journey, the amplitude of the signal detected by the ship is 0. So let's say the ship moves in a straight line from X all the way to Y. You can see that over here, when the ship is at this position, the path difference is still 0. And if the path difference is still 0 and the sources are in antiphase, the result will always be destructive interference. So the answer to this question is that all points are equidistant from P and Q, and therefore the path difference is 0. And since the signals from P and Q are initially out of phase, they will arrive at any point on XY in antiphase, and so destructive interference occurs. So you have to write destructive interference in order to score a mark, because what they want to see is the keywords, and one of the keywords is destructive interference. Okay, next, from Y, the ship moves towards Q until the signal detected had an amplitude about twice from either transmitter alone. Now we have to think about what does it mean by the amplitude is twice. The amplitude is twice means that it's constructive interference. Okay, now before we go any further, let's discuss what kind of a question is this. Now let's take a look at the structure of the question. We have two sources, P and Q, broadcasting the waves in every direction. Now they're broadcasting the waves in every direction with a wavelength of 300 meters. You'll notice that along this line, the waves from P are traveling in this direction and the waves on Q are traveling in this direction. That means to say, if the waves travel in the opposite direction with the same frequency and wavelength and they are coherent waves, they will superposition with each other to form a standing wave or stationary wave. So this is a stationary wave question. So a stationary wave question, and you know that at the position of Y, there is destructive interference. That means that this position is a node. Okay, now let's draw the stationary wave, okay, from P to Q. We're going to draw nodes every here and there. Okay, so this is one node, and here's another node, and here's another node. Okay, now we are going to draw the next part of the wave so that it's complete. This is the second half of the wave. Okay, of course the wave carries on after that. I'm not going to draw all of it. Now the question tells us that at this point Y, they receive 0 amplitude. So this is a node. And then it travels towards Q. When it travels towards Q, it encounters a place where the amplitude is twice. That means to say constructive interference. That means to say it encounters an antinode. Okay, so let's read the question again. From Y, the ship moved towards Q until the signal detected was constructive interference, meaning it is an antinode. Antinode, that means where the amplitude is a maximum. Calculate the distance moved by the ship. So how far did the ship move from the node to the antinode? Well, the wavelength of the wave is 300 meters. This is 300 meters. So if the wavelength of the wave is 300 meters, what is the distance between a node and an antinode? You can see that the distance between a node and an antinode will be 1/4 of the wavelength. Okay, 1/4 of the wavelength. Let me repeat again. The ship started off at Y, which it detected 0 amplitude. That means that it's a node. Then it moved towards a Q until it detected maximum amplitude, which is an antinode. So they asked, what is the distance between a node and an antinode? And if you draw the diagram out, you can see that the distance between the node and the antinode is 1/4 of the wavelength. So the new position is a point where constructive interference occurs, right? Basically, this is going to be an antinode. All right, so if you draw the diagram like this over here, like this, and then you draw, this is the position Y, and then this is the new position, okay? So they have moved 1/4 of a wavelength, which is 75 meters. Now you can see that when explaining it using stationary waves or standing waves, it is a lot easier than trying to explain it using phase difference and path difference. Okay, so I will recommend for you to explain it using the meaning of the stationary waves. So what I will write is the ship moves from a node to an antinode along the stationary wave. So hence the distance moved is lambda over 4. Okay, so that's what I would write as a response to this question. The ship moves from a node to an antinode along the stationary wave, hence the distance is lambda over 4, which is 75 meters. Okay, now next. The ship then sails to the harbor at Q. During the journey, the intensity of the detected signal fluctuated. Calculate the number of dips in the intensity. Wow. Okay, so this is going to be a challenging question. It starts off at Y, okay, and then the wavelength of the wave is 300, and there's a standing wave that develops along the way. Okay, so as you can see, it starts off, and then when it travels 300 meters, it encounters 2 dips. Dips meaning that minimum amplitude. So 300 meters is 2 dips. Now, it's going to have to travel, what's the distance to the speaker? It has to travel 30 kilometers, 30 km. So the question is, when you travel 30 km, how many dips are there? So if 300 meters is 2 dips, then 30 km will be 200 dips. Okay, 200 dips, which is a bit debatable. Is it going to be 200 dips or is it going to be 199? So this is something that we can discuss in class, because the last position of the speaker, is it going to be a node or is it going to be an antinode? That's something that we can discuss together. Okay, so this is how we do the question. First, we'll draw the number of dips as the ship travels from Y to the speaker, to the transmitter at, I believe it is a Q. Okay, so it travels from Y to Q. The Q is at 30 kilometers away from Y. So every 300 meters it travels, it will encounter 2 nodes. So when it travels 30 kilometers, it should encounter 200 nodes along the way, with the last node being at Q. Okay, so is it 200 or is it 199? Question mark. Okay, anyway, that should be the end of our superposition tutorial. Thank you. And please do ask me, oh wait, there's another question over here, question 18. Now, let's take a look at question 18. A speaker S is placed at the left end of a narrow pipe of 3 meters. When the speaker emits sound wave of 1.2 meters, the pipe was observed to resonate. Draw how the amplitude of the resultant sound wave would vary along the pipe. Okay, so 3 meters and 1.2 meters, let's find out how many wavelengths are there along the pipe. So L is 3 meters, wavelength is 1.2 meters, therefore the length L would be 2.5 wavelengths. Now, so we're not going to write 2.5 wavelengths. Instead, we'll write 5/2 wavelength. Now, this tells us that it's going to be the 5th harmonic. Okay, the 5th harmonic. So how do we write the 5th harmonic? Now, the boundary condition for the pipe that's open at both ends is antinode at both ends. The boundary condition being an antinode at both ends means that we'll put an antinode here and an antinode here. This will be the fundamental. Fundamental will have one node inside. Now this is the fifth harmonic, so we're going to have to add more nodes. Okay, so 1, this is the second harmonic, which is 2 nodes. This is the third harmonic, which is 3 nodes. This is the fourth harmonic, 1, 2, 3, 4, which is the fourth note, fourth harmonic, and then this is the fifth harmonic, 1, 2, 3, 4, 5. So let's draw the wave now, starting from here, goes through 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 here, and comes out here. To be sure that we have done this correctly, let's try to count the wavelengths, okay? We start from here. This is 1 wavelength, lambda. This is 2 wavelength, 2 lambda. And then over here, this is at the bottom, so that's 2.5 wavelengths. So that's 5 over 2 lambda. This is correct. Now, in order to finish the diagram, let's draw the dotted points. Okay, then we complete the next half of the wave, and now it's completed. The right end of the pipe was closed and the pipe stopped resonating. Yes, of course, because you changed the boundary condition to be a node at the right end. The frequency of the sound wave was increased. The frequency was increased. Now, if the frequency is increased, the wavelength is decreased. Until the pipe resonates again, determine the wavelength of the sound wave used. Now, in order to do this, okay, let's draw the pipe over here. This pipe will be 3 meters. 3 meters. Okay, so the pipe length doesn't change, but now the boundary condition will change. This is going to be the antinode, and this is going to be the node. Now, what we're going to do is that we're actually going to increase the frequency. When you increase the frequency, you're going to squash the wavelength. Okay, you're going to squash it. Okay, so let me just copy over this wave over here. Come on, behave. Okay, copy, and then I'm going to paste it over here. Now, what I'm going to do is I'm going to squash this wavelength until it forms a node on the right hand side. So I'm going to push this all the way in. Come on, behave, please. Okay, push, 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 push to the left. Oops, that's too much. Okay, let me squash it to the left over here. Okay, and then I'm going to complete the wave until it forms a node at this end. Ta-da! Okay, so this is going to be our new standing wave. Yay! The new standing wave of a higher frequency. Oh, good. Now let's count how many wavelengths are there in the tube. Okay, so over here is 1, 2, and this is 3/4. So it's over here is 1 wavelength, over here is 2 wavelength, and over here will be 2 3/4 wavelength. So 2 3/4 wavelength, let's change it to a nice harmonic number. So over here we're going to express this as 11/4 lambda. Yeah, 11/4 lambda, which means this is the 11th harmonic. This is totally unnecessary information, but it's cool to know how to do this. This is the 11th harmonic. So what is the wavelength of the sound used? Well, they're very easy. 2 3/4 lambda is equals to 3 meters, right? So the lambda will be 1.09 meters if you just divide 2 by 2 3/4. All right, so is any difficult calculation required? Not really, but your drawing skills have to be really good. Okay, so let me just repeat again the process of what I did. Basically, I know that when I close it, the right hand side has to be a node, and then the question says that the frequency was increased. Now if the frequency is increased, it means the wavelength is going to be squashed. So I draw the same diagram, but I squash it a little bit to make space. for a node. And then I count the wavelengths. Gotta be careful when counting them. You count it 1 wavelength, 2 wavelength, and 3/4 wavelength. So there's 2 and 3/4 wavelengths in the pipe. And so you can find the wavelength will be 1.09 meters. Okay, so over here you can see the thinking process for the stationary wave to be formed. For a stationary wave to be formed, the right end of the pipe must be a node, so the wavelength is squashed. So basically, 2 and 3/4 wavelengths are present. You cannot extend the wavelength because they say that the frequency increase, not decrease. Alright, so now this is really the end of the tutorial. The remaining tutorial are additional questions which you can ask me if you have any problems. And once again, please do approach me if you have any difficulty. Superposition is one of the more difficult topics in A-level physics. So you may not get it the first time around. Personally, I needed to have superposition explained to me 4 times before I understood. So if you're like me, please approach me if you need help. Thank you and have a nice day.